So we're going to do these notes here. We're going to learn about a new thing called power. It's an extension to what's happening with our type 1 and type 2 errors. Power is a good thing. Power is something that we want. It's going to help us to make a decision to reject the null hypothesis if we should reject it. Okay. But then also, as promised in our previous lesson, we're going to talk about the mechanisms that we have control over, or some things that we don't have control over, but those things that affect the probabilities of those events. Very important to understand how can we have an impact on those things we need to be able to control, or at least understand. So here we go. So now first we're going to kind of review. All right, so here is a picture here of the type 1 error. Okay, let's kind of revisit that. So what we've got, type 1 error, of course, that is the probability of the probability that you will be rejecting the null hypothesis when you should not. Okay, here's some other things that it is called. And so we can kind of think about that. Sometimes it's called a false alarm. Okay, false alarm. A false positive. Okay, so that's something interesting. Okay, for example, my friend was going to go and have foot surgery this past summer, and so he went to the hospital, and as a routine, they did a COVID screening on him to see if he had COVID, and they said he did. And so we were pretty much freaking out because of the high risk in our family and such, and that this was a person who had no symptoms whatsoever but tested positive for COVID. So we were very concerned about that. And of course, for that person, what's going to happen with that person as well. And then he couldn't do his foot surgery and so on and so forth. Well, he went back 3 days later and he had taken the test again and it was negative. And then again, and it was negative. So we feel fairly confident he had no symptoms. The first one we think it was a false positive, where we thought he had that, but he really didn't. Okay, so it's been really important though with this COVID. They've arranged the test so that they can have a high detection rate if you actually do have that COVID. So, we can talk about the mechanisms that change that. Now, other things that could happen with this, researchers think they have discovered a new medication that works or a new something that works, but it actually doesn't. It's the same as everything always has been. All right, so let's recall that our probability of a type 1 error is actually this area here that would lead us to reject the null hypothesis. So that's alpha, because if the null is really true, then our data would be located here around the null hypothesis. Okay, but we would, all of these samples that are naturally going to happen because of the normal model are here in this rejection region. So if your alpha is 5%, and this is shown as a one-tailed upper tail, but this could be reversed and think of it as a different direction. But I typically just kind of show it as this same way. Here, there's a 5% chance that you would reject the null hypothesis when you should not really reject it. Okay, so there's that. All right, now visualizing a type 2 error. So let's talk about that here, of course. So a type 2 error, of course, then is happening when you see here HO is false. And so therefore, see how I have no p hats in here? The data is not centered here. If HO is false, the data, the p hats, the samples are centered around where the alternative is located, wherever that is. I don't know. Okay, now let's think about if we're running this test. Here's our alpha. Okay, so you can see that what's happening is all of these samples then in this section here are going to give me the opportunity to reject the false null hypothesis like I should. And that is something new. That is called power. So we're going to come back to that in just a second because I want to review what you already know, which is that probability of a type 2 error. So that would be this little section here, of course, down here in this area, where these would be samples that are inside the alpha, not in the rejection region, but closer to the null hypothesis. So we would fail to reject a false null hypothesis, type 2 error, type 2 error. That is called beta. So this is kind of a new letter we're learning about. Alpha is the probability of a type 1 error. Beta is the probability of a type 2 error. Okay, now back to power. So power is all of these samples that lead me to reject the null hypothesis if I should, if it is indeed false. Okay, so here's some ideas about power. Let's take a look at these little things here to think of in terms of power. So it's the probability of rejecting the null hypothesis if it is indeed false. Okay, so doing what we should do, rejecting it. Probability of detecting if there is an effect, if there really is one. Okay, so we want to be able to, if nothing's happening over here in the null hypothesis, we want to detect that there is an effect going on. Detecting that the treatment is really having an impact on the data. Detecting that you have the disease if you actually have the disease. Okay, so that's where all of our data would be located over here to the right of alpha if you have that disease. Now, let's see here. I do have course, have a song for that. Here's our Hotel California. I don't have that queued up right now, and so I think I may just come back to that later. But it's so powerful. It's so dramatic. Power is the probability to reject the null, to reject the null if it's false indeed. Doom, doom, doom. Power is the probability. We want to really reject that null, to reject the null, to reject the null if it's false indeed. Okay, so we want to be able to reject the null and detect if the null is false. All right, so there you go. You got a little live version instead of the recorded one. Now, to our mechanisms of change. So here we go. I'm going to have to zoom out here so you can see this, and I might have to move my little video here. Okay. So this first mechanism that we're going to talk about is changing the size of alpha. So a couple of things to notice here. And I'm going to have to stick that over there so that I can use my tools to write with. Okay, so here we go. So alpha is something, first of all, foremost, alpha is something that researchers have an ability to control. You can, based on how, if type 1 error, you want that to be small, or if that's a really bad, if it's a really bad thing to have, type 1 error is really bad, then you want that small. But if having something else is worse, then you could afford to have a type 1 error if that's the lesser of the evils. Okay. So alpha being that size of the rejection region, that significance level, that probability of a type 1 error, you set that. So, our default is 5%. All right, so here I have two curves drawn here, and we don't really know. I did draw data in the right-hand curve as if HA is true, but we don't really know. Here is where we would have put where the data would be centered if HO is true, okay? So here's where the data would be if HO is true. So then here is our alpha. So if alpha is 1 or 0.05, I'm sorry, if alpha is 0.05, then we've got 5% of the samples that if we are not supposed to reject it, then we get 5% of the samples that would lead us to reject the null hypothesis. Okay, but what if we made alpha 10%? Well, then we now have 10% of samples. See, these curves are the same, but can you see I purposefully shifted alpha over? So that 10% of the samples now are causing me to reject the null hypothesis. So if the data is really located and the HO is true, if this is where the data is located, then the probability of rejecting that null hypothesis just went up. Okay. Now, let's take a look at the other mechanism, the other parameters that are happening. So, if we zoom in here, we can see, well, if we just kind of look in there, do you look at the type 2 area? I show that in orange. And I show that in orange on all of these slides. So I'm always going to show alpha in red, type 2 area in orange, and power in yellow. So look at the size of the type 2 area. When alpha increased, what happened to the orange type 2 area? It went down. It got smaller. Okay? So let's think about the other color, power. So here is our yellow area, that is power. And it's kind of hard to tell, but if, let's see if I can draw over it. So see if this is our power, okay? Then if alpha is bigger, then look what's happening with power. Power got bigger. So in summary, and by the way, I wrote up here in this top corner that you can see how these curves stayed the same size. They had the same variability from the top half of this page to the bottom half of this page. So what that tells me is that I did not change the sample size. I kept the sample size the same. The only thing that I changed was alpha. Okay, so let's summarize then what just happened. So we see that I increased alpha. So here I say with this I increased alpha, but I kept the n the same. So alpha increased, so the probability of type 1 error increases. We saw that beta went down. That's the probability of a type 2 error. It got smaller, but our power, it increased as well. Okay? And we're going to summarize all of these together later. Now, one other thing I want you to notice, and I forgot to mention it on the previous page, what do you notice about this relationship between beta plus power? What do you have to say about the total of beta plus power? Well, hopefully you can tell that's all the data. So beta plus power is 100%. So we typically don't do the mathematics of computing the value of power or beta straightforward. Usually, all that we're expected to know at this introductory statistics level is that those two add together to make 1. So if somebody had told me that the power was, say, if the power was 5%, then if, say, the type 2 error probability beta was 5%, then I could tell you the probability of power. I could tell you the probability of rejecting the null hypothesis because it is indeed false. I have a 95% chance of that because I know those two would add together to be 1. So keep that in mind also as we go through these. All right, moving on. Our next item of mechanism of change, the sample size. As a researcher, you have the ability to change the sample size. So we've talked about that a lot this year. What does increasing the sample size going to do to our sampling distribution? Well, you can see this in my picture. From the top half to the bottom half, the curves got taller and skinnier. And they got taller and skinnier because as n increased, the standard deviation went down and got narrower and skinnier. Okay? So that in turn then is going to affect our probability of our events, type 1, type 2, and power. So let's take a look at those. So up at the top, let's first talk about type 1 error right off the bat. If the null is true and the data was centered here in the left, okay, then here, let's say we have alpha is 5%. So then we have 5% chance of a type 1 error. Now, I'm not going to change alpha. The only thing I'm changing is sample size. So I still have this test with alpha being 5%. So in essence, though, see, look at this. This alpha is still 5%. So my probability of type 1 error stayed the same. Okay, that was actually not impacted. So it stayed the same. But I can tell that because my samples squinched in and they got more closely clustered around their center, then suppose that the data is centered around HA. So if the data is centered around HA, then by increasing your sample size, the data is even closer around HA. It sucked this area in. So look at how much type 2 error there is. Basically nothing. Look, there's like, type 2 error is, I want that in orange. Type 2 error is, any of our samples that are over here to the left of our alpha. Well, they're so far now separated, these curves, there's probably not even any data over there, okay? So, but depending, there could be, depending on how close the HA is. But at any rate, it has definitely made this probability of a type 2 error smaller. So by sucking those in, we have now increased the probability that we're going to reject the null if it is indeed false. So we've increased power, and of course, those two add to 1. So if power goes up, then beta goes down, always. They are inversely related, always. So let's summarize this. Here we go. Let's see. So in summary, we increase n, but alpha stays the same. So our alpha stayed the same, so therefore our probability of a type 1 error stayed the same. Okay, so if the null is true, then we still have the same probability of type 1 error. But sucking that data in, if HA is true, then we have now decreased the likelihood of having a type 2 error, which then increases that power, increases the probability of rejecting that null hypothesis if it's false, increases the probability of detecting that there is an effect if there really is one, increases the probability of detecting that the treatment works if it really does. Okay, I'm trying to say all those synonyms, those things that say the same. All right, now this last mechanism of change, researchers actually don't have control over this. This is just, where the data falls. Is the medicine highly toxic? So it is way far away from the null hypothesis? Or is it just a little toxic? then your data is going to be close to the null hypothesis. Okay, so this is called an effect size. The effect size is the effect, it's just kind of that location of the data that is affected. Okay, the location, the natural location of the effect. So, again, researchers don't have control over this. All right. So let's take a look at what's happening and how things are affected. So here we go. First, you know, okay, alpha is staying the same and our sample size is staying the same. So do you see my curves here from the top to the bottom? Do you see those curves are the same spread, same variability? Okay. Now, do you also see that alpha stayed the same? Okay, so I did not change those. So this is only affected by how far away the data really was. And so our type 1 error is going to stay this 5%. So if the null is true, then that's where our data is. Okay, that our data is here. So alpha not changing, we still got the same old rejection region. Alpha probability of a type 1 error stays the same. However, if it's not true, then can you see what's happening down here on the bottom? We've got the data farther away from the null hypothesis. So by it scooting over, look what has happened to type 2 error. Here's this orange area for type 2 error that has pretty much gone down. I'm exaggerating it here and showing that it's gone down to almost nothing. So that type 2 error is decreasing, which I think makes sense. If the data is so far away, so because it is so toxic, then it's going to not be very likely that that you don't detect the toxicity. So your power is really high. If it's very, very effective, if the treatment is really making a difference, then you're probably going to be able to detect that it is making a difference. So that power increases. So in summary, then what we have down here in the bottom is, if I can show you that, of course, our alpha stayed the same. So our type 1 error probability stays the same, but that type 2 error goes down and power goes up. All right. Now, here is a way. This is not a standard thing. This is a Miss McClellan thing. Trying to figure out a way to how could students just like draw something real quick to um, help them quickly remember how all of these things are related. So here's the first. I'll show you this, and then I'll show you how to work this visual aid. Okay. So first, the things that we're going to do is talk about the ways to, this is going to talk about the ways that we are changing power and type 1 error, type 2 error. So over here on the left, I've got this. Alpha is type 1 error, okay? The probability of a type 1 error. Beta is the probability of type 2 error. Now, we frequently have control over sample, or we can control the sample size, which is affecting that standard deviation, so that's reminding us that it's making those smaller. Now, I don't know if I like this green thing in here. This is new this year. I just added. This is actually the effect size. And so I am showing you what's happening if your HA is farther away, you're having more of an effect. Farther away from HO, you have more an effect. So there's the mechanisms. Now, I highlighted in purple these two things here, alpha and N, because those are the two items that the researcher has ability to state and control and go find sample size. Okay, so those are the things that we actually can control. Okay. So then what I do, and actually I think what I want to do is show you this writing in real time. So let me put a blank page here. And so here's how we might do it. I like to say this. I like to say, okay, we got alpha is a probability of type 1 error. Okay, we got beta is the probability of the type 2 error. N, sample size, affects the standard deviation. Okay. Oh, I usually circle these together. Okay. All right. So there's how I start. Now, what I want to do is talk about the ways to affect power. So I write power up here at the top. Okay. So there is my starting point. Now, you're going to draw in your arrows of change. Let's draw in arrows of change. I think I'm going to do this in pink. Okay, so here comes the arrows of change. Over here, if I put an up arrow on the left, then I'm going to write the word increase. So, and then I'm going to do a down arrow on the right. So let's talk about what this means. Okay? So if I was to see this picture, this tells me, hey, if alpha goes up, look here, if alpha is going up, then guess what? I know power increases and type 2 error goes down. Okay? Now, these are separate. I mean, alpha is not affecting N. Okay? Remember that, you know, this here and this here, those are your mechanisms that you can change. And then everything else just happens. Okay? So I'm not changing this bottom circle if I'm only changing alpha. So let me say that all again. Let me take back these things here. Okay, so let's say that I decide to increase alpha. Then I'm going to draw an up arrow on the left. That is increasing power. Okay, and if we go up on the left, we're going down on the right. So type 1 error probability goes up, type 2 probability goes down. And remember how beta and power, those are inversely related. See, power is increasing, beta is going down. Okay. Now, what happens if I decide to change the sample size? Let's go with this. Let's say I choose to make my sample size go up. N increases. Well, okay, that's not going to change this red circle here, you know. Sample size doesn't change alpha. Okay. But you know what N does change? It changes this standard deviation. So then all these other things happen. Power increases and type 2 error decreases. Okay, so let me say all that again. So if I decide to change sample size, if it goes up on the left, so N is over here on the left, so up on the left, that increases power, decreases beta. And that's all happening because that standard deviation is going down. Okay, so what you can do is the reverse of this picture. So let's, draw it again. It's always good just to practice, okay? So let's do it one more time. Let's put our alpha and type 1. Okay, our beta is probability of type 2. Okay, our N affects standard deviation. Okay, I didn't do my circles. And then, of course, you remember up here at the top, we've got power. Okay, so let's put in our arrows. So let's say that we decrease alpha. So I'm going to draw a down arrow on the left. That's going to decrease power. Down on the left is up on the right, so type 2 went up. Down on the left, type 2 goes up. Okay, so that's what's happening there. Let's say, see this also, if say I made my sample size go down, say you decreased your sample size down on the left because the sample size went down, that decreases power. Whatever this is word here, that goes with that arrow. Decrease goes down and the type 2 error went up. That's how that works. So you can see down here at the bottom of this key here, I have those two situations drawn, the increasing power, the decreasing power, and those arrows. Now, I also knew this year added, and I think it might be just too confusing, but it's in here just in case you want it, that these are the effect size, which we don't have control over, okay? You know, the farther away it is, that's a good thing because the farther away HA is, we then have all this power to detect an effect. But here, look, if HA is closer to HO, we don't have, it's going to be difficult to detect an effect. So that decreases our power. Okay, big video on all of that, mechanisms of change and their summary. The last page is kind of short. It's got one page of examples and such, but I'm going to separate that into a small, short secondary video for these notes. So we'll go ahead and stop this summary here, and then I'll meet you in the next video to go over the practice putting this into play into real world context. Okay?